So we're going to continue with atomic structure and periodicity, and those two really go hand in hand. And it should become obvious as we progress through the rest of this chapter how closely they are related. Okay, so I'm gonna get started and pick up where we left off, and I'll call your attention to a couple of things on the way. Let's see, where am I? Well, why is it not showing? Technical difficulties. Hold on a second here. Try that share again. There it is. Okay. And let's see. Start the slideshow. The only reason I'm going to start the slideshow from the beginning is so I can show you some changes that I've made. Some of the things that we discussed during the last lecture, I said I need to put some more stuff in the PowerPoints, and I've just added a few things, and Blackboard has the updated version. So if you want to go back and take a look at some of these things, they're not earth-shaking, but they do sort of on occasion flesh out the topic a little better than I did, or than the PowerPoints prior to this one. Yeah. So we've covered all this stuff up through photoelectric effect. Okay, and here's some points that I made during the lecture that I decided I would put in the PowerPoint slides so that you'd have a permanent record. Okay, so eventually I'm going to get to Heisenberg's uncertainty principle. Let's see. We're getting close. Let's see, there's the Bohr model. And I just noted that in their discussions, the authors left out the violet color. And I discovered that the transition for the violet is from level 6 to level 2. The other three colors are all to level 2, and the violet is also to level 2. This might be need to make a point of this one. When you're calculating the energy transition from one level to the next, the slides in the original set were just woefully inadequate. So I inserted these extra slides, and the point is that when you're calculating the energy of an electron at any given energy level in an atom, you need to know two things. One is you need to know this value here, which is the whole number multiple energy level 1, 2, 3, 4, whatever the case may be. But you also need to know Z, which is the number of protons. And for the hydrogen atom, the value will be 1, of course. So that's why when you calculate for the hydrogen atom, that 1 is always there. But if you want to calculate a transition from one to the other, you need to know the final energy minus the initial energy. And that's why you get the final version here minus the initial version here. And this version actually works for any element as long as it only has one electron. So for everything but hydrogen, you are creating an ion in order to make this equation work. So for helium, it would be a +1 charge. Helium atom or helium ion would be valid for this formula. And for the Z, you would have to put in 2 because helium has 2 protons. And that's true for any of the elements. You have to strip off all the electrons but 1 before this formula will work. Okay. And I think there are some problems like that in your review document, at least one of them, that asks that question. And we went through this one last time where it wasn't really clear how we arrived at the, actually we went backwards. Instead of going forwards with the analysis, we took this this formula for the energy, H nu, and calculated what would be the energy transition for that wavelength. So we converted the wavelength to an energy and compared it to the calculation that we had done for the transition from 5 to 2 for the hydrogen atom, and found that they were very close to one another. So it's just confirmation that this Bohr formula works. Okay. So yeah, that's to me. Okay, so here's where we stopped the last time with the Heisenberg uncertainty principle. There were a whole host of scientists at the beginning of the 20th century working on this problem because the Bohr model just did not satisfy. It was a good starting point and it has limited application. But the character of an electron as both particle and wave was not resolved yet. We couldn't marry the two. And with Heisenberg's uncertainty principle, he said this is why you can't, it just doesn't work, because you cannot simultaneously know both the position of the electron and its momentum. And when we say momentum, that includes mass and velocity. So if you want to know one, you've got to give up the other one. And that's what made it so difficult to marry the two concepts of the wave nature and the particle nature of electrons. So there were a lot of people working on this problem, and it took decades to really put together a workable theory. And that turned out to be, and the model that goes with it, of course, and that turned out to be the quantum mechanical model. So no one person really can take credit for it. You have some pretty big names in there. Max Planck, we know about him with Planck's constant. Albert Einstein, of course. Louis de Broglie was instrumental in adding to the concept that would become the quantum mechanical model, and all these others. We're going to talk about Schrodinger in just a minute because it has to do with the wave function. And I know that doesn't mean anything right now, but it will. Some other big names: Max Born, Paul Dirac, Wolfgang Pauli. We'll encounter Pauli in a few minutes also. But there were many others. So I just threw these names out there just to pique your interest, if for nothing else, no other reason. Okay, so for very small particles, these terms in this equation become extremely important. For objects that are as big as we are, like humans, it doesn't matter, because the variability is overwhelmed by our mass. But when you get down to that very small size, then these terms really make a lot of, have an impact on describing the electron. And notice that the only, well, you have pi here, of course, which is, you find it a lot of places, but really the only term that Heisenberg was concerned with was the, shake my brain, the Planck's constant. Okay, so to make a long story short, Schrodinger came up with a set of equations, and they were refined over the years, that described the probability, let's put it that way, the probability of finding an electron in a given space around an atom. Because that's all we can do. We can't say the electron is exactly there. We just have this wave function that fits into an equation and gives us a distribution, a possible location for the electrons. And that's important to know, because where the electrons are has bearing on how atoms interact in a chemical reaction. Because think about it, when two atoms approach one another, what do they see first? They see electrons. They don't see nuclei. So knowing where the electrons are, how dense they are in a given region, is extremely important for predicting how chemical reactions will proceed, if at all. So this wave function, and that's another important distinction to make. Whereas the Bohr atom had a nucleus here, and then it had orbitals. Bohr was saying that the electron occupied these orbitals and no other place, nothing in between, which was really an insightful comment. But the fact of the matter is, since we don't know where they are, another approach is to view the electron in that space as a wave and not as a particle. So this is the Greek letter, the capital Greek letter psi, psi, which is used to stand for the wave function. And it's helpful to think of electrons in terms of a wave. So at this energy level, there's your electron. It's a wave at that energy level. So what use is the wave function? Well, if let's see, who was it? Did I put his name here? I don't think I did. There was another scientist who says, here's the significance of that wave function. If you square it, the square of the function is an indicator of the probability of finding an electron in a particular point in space. So it's part of the probability function. So if we graph it, we find that for this particular electron, as you move further away from the nucleus, which is on this axis, the distance from the nucleus, then the probability of finding the electron there decreases. All right, so this must be energy level 1, because it's going to be its highest density closest to the nucleus, not on the nucleus, but very close. So they actually left out a little bit in here that should have been 0, because you're not going to find electrons in the nucleus. So there should have been a space in here for 0, but recognizing that as a fault of this representation, the density, the possible density or probability of finding an electron close to the nucleus is very high for this energy level. And that's what that graph represents. Okay. So we've corrected it here for this one, and we find that at the nucleus, of course, the probability of finding the electron there is 0. You're not going to find an electron there, but it peaks at a certain distance from the nucleus. Now that's not exactly where energy level 1 would be. It's where you're most likely to find the electron at that energy level. And then it trails off as you get further from the nucleus. Okay. So a word about orbital size. We're speaking of this space that electrons occupy as an orbital. And that's kind of a holdover from the Bohr model, because the Bohr model was based upon the concept that electrons go around the nucleus like planets go around the sun. So we still call it an orbital, even though we know it's really not, it's not like a planet. We can't define precisely the size of the orbital. All we can do is give probabilities. And this imprecision in our knowledge of where the electron is and what it's doing there is one of the hallmarks of quantum mechanics. Quantum mechanics is basically a set of probability equations. Right? That's what gives most students trouble, is coming to terms with the fact that it's not like classical physics, where you have a mass, and if it's going that fast, then it has a certain amount of energy. In quantum mechanics, everything is probability based. And the orbital itself is a wave function. So that's why I sort of drew it like a wave, overlaying the Bohr model. It helps if you can visualize these orbitals as a three-dimensional sort of a density map. You know, a density map, I can only show you in 2 dimensions here, but a density map would be like very high density there, lower density there. So it's like the number of dots per square inch would represent a higher probability of finding the electron in that space. That's what they mean by a density map. So we're going to use a terminology here that we haven't defined yet. So give me some latitude. The hydrogen 1s orbital, which is the very lowest energy place, and that's where the electron is for the ground state of the hydrogen atom, is in this particular orbital. And this terminology, 1s, will become useful in just a few minutes. What we can say is that within this space that we've defined as the orbital, this probability density map, there's a 90% probability that you'll find the electron in that space. Of course, there's always probability that you'll find it someplace else. I had a professor as an undergraduate who explained it this way. He says, there's a very, very tiny probability that all the air in this room will migrate to that corner and will suffocate. I mean, it's true. It's statistically speaking, the probability exists, but it's unlikely to happen. Okay, so let me see if I can get this thing moving again. There we go. So we introduced the concept of quantum numbers. Quantum numbers are used to describe an electron in an atom. Now, the quantum number itself is not a description, but it fits into a wave equation, these four numbers. There are four of them. They fit into the wave equation, and once the equation is resolved, then it produces that density map, that distribution. But in order to describe the electronic configuration of all the electrons surrounding an atom of any given element, we need to know those four numbers. Okay, so now we're gonna define what those numbers are. Okay, we've already talked about the energy levels for the Bohr atom, and that relates to the very first quantum number, which is this little n. So don't get that confused with moles. I know I use little n for moles when we're doing stoichiometry, but now we're talking about electronic structure, and the little n is the principal quantum number. And it relates to both the energy of the orbital, you know, the higher the number, the further away from the atom it is, and actually relative to the nucleus, it's a higher energy. But it also describes the size of the orbital. Right? So the higher the number, the bigger the space that's occupied by the probability density map for the electron. And it can go up as high as you want it to. Now, as a practical matter, you only need a certain number of them to completely fill the periodic table. Right? So theoretically, it could be, n could go as high as you want, and I'm sure some theoretical chemists, physical chemists, go very high just to satisfy their curiosity. But for our purposes, let's see, 7, I think 7 is as high as you need to go for these numbers. Okay, you need to know that number. Now, from that number, you can derive the next level, the angular momentum quantum number, or L. And L is derived from N, and you can have as many L quantum numbers as the size of the N is. So let me explain that a little differently. Let's say we're at, we have an electron at N equals 3. Okay, I don't want to use black. Too hard to erase. Okay, how many L possible orbitals can you have at the N equals 3 level? You can have 3 of them, right? And they can have numbers starting with 0. Okay, so if N equals 3, you can have 3 L's starting with 0, 1, 0, 1, 2. Okay, if you had 4 here, you could go 0, 1, 2, 3. If you have 2 there, then you can only have 0 and 1. And if you have 1 there, you can only have 0. Okay, that's the angular momentum quantum number, and it's used to describe the shape of the orbital. If it's a 0, then it's spherical in shape, like that. If it's 1, then it's kind of a dumbbell. Okay, and if it's 2, it gets weird. So I'm not even going to bother with that. So a pattern may be developing in your mind that each of the next levels, starting with the quantum level, the next level, are all based upon the level before it. So the principal quantum number n gives you information that you need to define what are the possible angular momentum quantum numbers. And then the individual L numbers will give you information that you need for deriving the magnetic quantum number, the M sub L. Now this one describes the orientation in space of the orbital. And that's important for knowing how atoms will interact when they approach one another in a chemical reaction. If the electrons that are going to interact are facing off this direction, then it's unlikely that they're going to give you the reaction that you're expecting. So we've got the N, the L, and the M sub L, magnetic quantum number, defining the orientation of the orbitals. And when you have an L number here, let's say 2. If L is 2, then you can have magnetic quantum numbers beginning with negative, let's see, you can have negative L. Yeah. You can have, let's say 1. 1's a better choice. I don't want to get too complicated early. So the M sub L's, the possible M sub L's would be -1, step up to the next, 0, -1, 0, +1. So out of this 1, you can get 3 M sub L's. Let's go ahead and do 2. If you had 2, then you could have -2, -1, 0, +1, +2. So you could have 5. 5 possible M sub L's out of this 1 L value. So that's 3 of them. Actually, the 4th one is the simplest. The M sub S is simply the electronic spin quantum number. And it can either be +1/2, -1/2. And within any M sub L, whatever it happens to be, you can only have 2. Right? So let's just say it's, from that previous example, is -2. Right? Within that one, you can have a +1/2 and a -1/2. That's it. For any of the M sub L's, you can only have 2 M sub S's. Okay, so there we have it. We've got our principal quantum number, our angular momentum quantum number, our magnetic quantum number, and our spin quantum number. Those 4 numbers define an electron. And yeah, I don't want to jump ahead. So let's just take it slide order. So here's a chart that came straight out of your book, or at least one edition of your book. And it shows the relationship with n equals 1, you can only have 1 L. And you can only have 1 M sub L. And that means the number of orbitals possible at the n level is only 1. But if you have n equals 2, then you could have 2 L's, and you could have 1 M sub L at the 0 L and 3 at the 1 value of L. So that means you have 1, 3. So if we have an atom that occupies the first two energy levels, you can have a total of 3, 4, 5 possible orbitals. And remember, after you get to m sub L, you can have 2 electrons in each one. So once you get to 5, you can have 10 electrons at that position. Okay, I'm not going to hammer that nail too hard right now, because once we go through the process of building the electronic structure of an atom, I hope it'll become clearer. There's one convention that's used in order to make writing the electronic structure a little easier, is the adoption of these letters, S, P, D, and F. And they refer to values of L. So if your L is 0, then the letter for it is S. If your L is 1, it's P, 2 is D, 3 is F. Now for ground state atoms, that's as many as you need. That will cover the entire periodic table. You only need higher levels. You could go up to G. You only need higher levels if you're going to excite the atom and promote electrons into higher energy levels. We're not going to do that right now. Maybe later. Okay. So let's take this example. And I just know I'm going to run out of time. So I'm going to spend as much time as necessary. And if you have to leave, same policy as always. It just might bleed over into our, so this is Tuesday. Yeah, it'll bleed over into my office hours, but that's all right. I'll just keep talking until the chapter's finished. And you can view the recording later. For this example, the principal quantum number, say, is n equals 3. So how many subshells? And a subshell is a term that's used for the L value. Right, the momentum quantum number, angular momentum quantum number. So how many different values of L can we have for the, well, how do we do that? Well, you take the n and you start from 0. So we have 0, 1, 2, that's it. You can only have 3. And 3 subshells, 0, 1, 2. So that means S, P, and D. 0, 1, and 2, S, P, D. That's how they go. Okay. So for L equals 2, determine the magnetic quantum numbers and the number of orbitals. So for L equals 2, you can have -2, -1, 0, 1, and 2. Okay, so you can have 5 magnetic quantum numbers for the number 2, or the D angular quantum number. So you have 5 orbitals, and just as a teaser for the next few slides, that means you can have a maximum of 10 electrons in those 5 m sub L's, because each one can have 2 electrons, plus 1/2, minus 1/2 spin.
An s orbital has a spherical shape with the nucleus at the center.
So these next little videos, short videos, are just going to give you an idea of what the shapes are. So remember, the shape is related to the angular momentum quantum number, or the L value. So this L equals 0, which is S, is a spherical shape. At any energy level, it's always spherical shape. Okay, this is one way to look at it. 3 different ways to look at it. You can have this surface model right here, spherical. The 1s, of course, only has the 1s orbital level, whereas the 2s has a spherical shape, but it also has a region in there where there is no electron density predicted. Call it a node. So for the 2s orbital, we have 1 node, 2 minus 1, 1 node. This plot shows you that node right here. Okay, notice that the 1s has no nodes. And we're discounting the 0 probability at the nucleus. We're not calling that a node. And if you go up to 3s, you have 2 nodes, 1 there, 1 there. Okay, this is a consequence of the quantum mechanical wave function equations that are solved, and when they're solved, they produce this distribution. Now, what is this? The solution to these wave equations is only valid if it's able to explain the structure of the atom and its chemical behavior. And thus far, the quantum mechanical model of the atom has been successfully used to explain a whole host of behaviors. That's why it's still valid. If it didn't do that it didn't do a good job of explaining these behaviors, chemical behaviors, then remember what we would have to do, right? Either throw it out and start over, right? Or you modify it, and many modifications have been made to make it work better. Or you restrict its use. You say you can only use it under these circumstances. And there's a little bit of that also. Okay, so let me proceed to the next.
The 2px orbital is in the shape of a figure 8 along the x-axis.
So there's that dumbbell shape I was talking about earlier. So the p orbitals, or the L equals 1, are dumbbell shaped, with, of course, the nucleus is right here at the center.
The 2py orbital is in the shape of a figure 8 along the y-axis.
Okay, now why are we getting the same shape of orbital in a different direction? Because of the m sub L number. Remember, the p refers to L equals 1, and m sub L then is equal to -1, 0, plus 1. So I'm not sure which one refers to which, X, Y, or Z, but you're going to have 3 of them. So one of them points along the x-axis, one of them points along the z-axis, one of them points along the y-axis.
The 2pz orbital is in the shape of a figure 8 along the z-axis.
Okay. So that's the, this is 2 ways of representing it, right? You could just have a, this is a scatter plot, is what they call that, of possible locations for electrons. And this gives a general shape. It's not as pretty as these others.
The 3dx squared y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
Okay, so now we're talking about the D, where L equals 2. And that means m sub L is going to be a -2, -1, 0, +1, +2 possibilities. So this will be not only a directional difference, but there'll be slight shape changes as well. And you'll see that. So we've got one covered. There are 4 more of them that are designated D.
The 3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y axes.
The 3dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z axes. The 3dyz orbital has a cloverleaf shape that lies in the yz plane and bisects the y and z axes.
Okay, so that's 4 of them. And they're all cloverleaf up to this point. But there's one more that's kind of weird.
The 3dz2 orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z-axis.
Now these shapes, the quantum mechanical chemists who solve the equations and show us these shapes, these are based upon the wave function equations that give us these distributions. So it's not like they pulled these shapes out of thin air and then tried to force the formulas to fit to them. This is what they derived once they solved the equations. And these are just other ways of representing them. You're not going to have to reproduce any of these shapes. I'm more interested in your ability to actually write the electronic configuration for an atom. And we're going to practice that in just a minute. Now there's the F's, right? If the F is 3, then we're going to have 7 possible M sub L's, right? So you should see 7 representations here of the F orbitals. Okay, we talked about electronic spin. There's that number. And it leads us to the Pauli exclusion principle. I mentioned Pauli earlier with some of the scientists that were central to development of the quantum mechanical theory. And Pauli was one of them. And his exclusion principle just says, in any given atom, no 2 electrons can have the same set of 4 quantum numbers. In other words, the set of quantum numbers is unique to every electron. Now, it's possible that the N, the L, the M sub L can all be the same numbers for 2 electrons. If that's the case, then they have to have different spin quantum numbers. And that's when you fill an orbital with the same quantum numbers as their first 3 numbers, then the only way that those 2 electrons can be inserted into that orbital is if they have opposite spins, +1/2 or -1/2. Okay, so the hydrogen atom is what we would call a monoelectronic atom. And ions that only have 1 electron in their orbitals surrounding the nucleus, those are monoelectronic atoms. But most elements and most ions in the universe are polyelectronic atoms. They have more than 1 electron surrounding the nucleus. And it's impossible. Let me just put it that way. It's impossible to calculate how these electrons will interact, right? Because they're all negative charges and there's some repulsion. That didn't go away with the quantum number, with the quantum mechanical model. You still have the electron repulsions that are there, and they influence how the energy levels are positioned around an atom. Another way of saying that is you might have an energy level of N equals 2 with sublevels like m sub l's and so forth. But if there are other electrons in that region that have to be accommodated, those energy levels might shift based upon the repulsive nature of those electrons in their regions. So that's when it gets really complex really quick, trying to define what the true shapes and densities of these orbitals are when you are trying to fit lots of extra electrons in there. But we can say this: as you're building atoms, hydrogen, helium, lithium, beryllium, boron, right on up, as you add electrons to that electronic structure, the electrons prefer to enter into the lowest available orbitals. And I mean that in terms of energy. The lowest possible energy is where they like to reside, and that's the ground state. And they prefer the orbitals in sequence from S, P, D, and then F. So beyond the principal quantum numbers of 1, 2, 3, 4, 5, 6, 7, then within those, they prefer to insert into S's first, P's next, D's next, and then F's, if they're available.
In a hydrogen atom, all subshells for each N are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
Right, so that's what I was talking about earlier. You may have noticed that we'll focus on this one, the principal quantum number 2, where you have available S and P's, right? Once you start filling electrons into those orbitals, they interact with one another, and that effectively changes the energy of those subshells. And notice that when we started doing that, the 2p rose, as did the 3p and the 3d. They increased in energy. That's because when you start repelling one another, then you're adding energy to the system, and that drives the subshells energy levels up. There's an effect called and this is, it's difficult to just go splash it right in front of your face, the penetration effect. I'll try to explain it. We can say that the 2s penetrates to the nucleus more than an electron occupying the 2p orbital. And that has to do with a number of things. One is the shape. Right? The shape of the s orbital is spherical. Right? So the density of electrons is concentrated more closely toward the nucleus, whereas the 2p orbitals are dumbbell shaped, and that tends to stretch their electron density out away from the nucleus. So we would say the 2s electrons penetrate to the nucleus more than the 2p's. That causes the 2s orbital electron to be more strongly attracted to the nucleus than the 2p's. And another way of saying that is that the energy of the electron in the 2s is lower than the 2p's. Remember, we measure electrons based on how close an electron is to the nucleus. And we give those values negative numbers because our zero value for energy of electron relative to nucleus is infinity. That means an ion is formed. The electron is completely stripped away from the nucleus. Now, relative to that nucleus, the energy of that electron is 0. which just means if the electron is starting at the 1s orbital, the very lowest possible one, then we have to add a lot of energy to remove it from the electron. And it goes from that negative value all the way to 0, which is an input of energy to get the electron away from the nucleus. Whereas with a p orbital, which is only, they start to be available with the n equals 2. You don't have any p orbitals in the n equals 1, right? Because there's only one possible orbital. It has to be s. But with a 2, you can have s's and p's. Well, with the 2p orbital, if there are more than one electron in the region, then the p tends to shift higher in energy, further away from the nucleus, which means it takes less energy to remove a 2p electron than it does a 2s electron. And that varies, of course, with how many electrons are there, right? Because the 2p orbital can have 3 m sub l's, and each of those can have 2 electrons, so there are 6 possible electrons. If it's completely filled, then you've got a lot of interaction going on in there. And we'll talk about that a little more later. You can see the penetration effect with the 2s in another way. Remember we talked about the node. There's the node for the 2s, the 2s orbital has a node there. It's still spherical, but there's a node here, but there's also extra density down here. In spite of the fact that most of the 2s density is out here, you still have some down here. So this may be easier to visualize as the penetration effect of the 2s versus the 2p, because the 2p doesn't have a node except at the nucleus. So most of the density for the 2p is here, which would appear to be at a lower energy than the 2s, except for the fact that the 2s has a significant density here close to the nucleus. And then when you get to 3s orbital, you have 2, and you still get some penetration with these lesser densities down here on either side of their nodes. Now, if we compare the 3s, 3p, and 3d, actually the 3p does tend to get a node here. And that's a little hard to explain, so I'm not even going to try. But you get penetration in this case, not just from the s orbital, but you also get some penetration from the p. The p orbital penetrates. So relative to the d orbital, the p penetrates below the d, and for many atoms, the p will have a lower energy than the d. There are some cases where that flips, and we'll have to talk about that later. But it's all based upon these wave function equations. Once they're solved, then you can say something about the actual energy levels. And believe me, before the advent of supercomputers, the solution of one of these equations was an extremely long and laborious process. Before you even had calculators, you had slide rules, and the solution of the problem for many atoms was impossible. You had to just work with the lower Z number atoms, like hydrogen, helium, lithium, and it becomes extremely difficult without supercomputers. Okay, let's talk about the periodic table. I got 15 minutes left, and I know I'm going to make it, but I'm going to get started. So, why did the periodic table develop? I mean, what are its roots? Well, there was a German chemist, Johann Dobereiner, in the middle of the 18th century, who observed that there were groups of elements. He called them triads that exhibited similar chemical properties. And we use the chlorine, bromine, iodine here as an example. These are halogens. And we all know that halogens behave similarly when they react with metals, particularly the alkaline metals. And he noticed that for several different groups, right? So there's just an observation, and he let it go there. It wasn't until two other scientists started observing these relationships in more than just three triads, not just the triads, but in more than one element, were exhibiting similar properties. Another German, Julius Meyer, observed that, and also Dmitry Mendeleev made that observation. Now, we give credit to Mendeleev for the periodic table primarily because even though both Meyer and Mendeleev grouped elements by their chemical behaviors, Mendeleev took it one step further. He used that information to predict the existence of elements that were not yet discovered. And that predictive power of his periodic table is why we give him credit as the father of the modern periodic table. Because those elements were eventually discovered, and they possessed properties that Mendeleev predicted, including chemical properties and physical properties. Wherever he was able to do that, he made those predictions. Okay, so let's see. I'd like to talk about, well, let me just say this. Mendeleev's original periodic table had the groups horizontally. So he would put fluorine, chlorine, bromine, iodine in a horizontal row. Those were the groups. That was his first publication. His second time he republished his periodic table with more elements in it. He rotated it 90 degrees. So now the groups were vertical. And then over the decades, a refined structure to the table was developed, which took advantage of the electronic structure of the atoms themselves. And that's why, I'm going to skip over these and go back over here. That's why the table is grouped in such a way that the orbitals of interest, the ones that are being filled from left to right in this region, are the p orbitals. So this element will have one p electron. This one will have 2, 3, 4, 5, 6 p electrons when you get over to the far right in the noble gases. On the left-hand side, only the s orbitals are filled for these, the alkaline metals and alkaline earths. And then the transition metals are all filling d orbitals. In other words, everything below that is already filled. And now we're adding electrons into the d orbitals for left to right, going across like that. And then, of course, for the f orbitals, the lanthanides and the actinides, which fit right in here. But it makes more sense for shrinking the table and for calling attention to the fact that the lanthanides and the actinides are being filled in their f orbitals. So that's a second reason for pulling this group out of the main body of the table and putting them separately. Okay, I wanted to get that in there before I talked about anything else. Okay, the Aufbau Principle. I don't know German, but I'm told that Aufbau means something like, here's how you do it. The Aufbau Principle states that when you add a proton to go to the next element, then you add another electron to it. And when you add that electron, it enters into the next highest energy level. It doesn't go way up high, it goes to the next lowest available energy level. That's what that means. And there is a sequence of orbitals that are available that you fill. And they're not numerical and alphabetical necessarily. For the smaller atoms, yes, they go in sequence: 1, 2, 1s, 2s, 2p. And then once you start getting into the higher levels, then you have to backtrack some because of the energy level restrictions on where those electrons can go. And we have a, let's see, where is it? Here it is. This shows you how that goes. Right, we'll get to that later. But for now, this is an example of filling and writing the electronic configuration for oxygen. Because you're going to have the 1s first, then you're going to have the 2s, and then within the 1s and the 2s, you have the subshells, the L's. Right? So you always start with 1s. And then the next level is the 2s, and they also have S's and they have P's available, right? 2 can have 2 subshells. So 2 can have a 0 and a 1, an S and a P. And then you can go to 3S, 3P, 3D, right? 3s can have 3 levels. Then within each one of these, you could have sublevels, the M sub L's. Right? S's, they don't have subshells, sublevels. P's, you can have 3s. You can have what we call X, Y, and Z. The D's, you can have 5, right? And I don't have designations for that, but you can have 5 total sublevels, which means what? 10 electrons. So if you fill this one to the max, how many can you have? There's only 1 subshell, so you can only have 2 electrons, plus 1/2, minus 1/2. So you can have a maximum of 2 here, a maximum of 2 there, a maximum of 6 here because 2, 4, 6, and a maximum of 10 here. 2, 4, 6, 8, 10. 5 subshells, 2 each. Right? So those are the maximum. Now, when would we have maximum in a P? Noble gases. That's when the P is completely filled. Okay, so let's go back to oxygen. Oxygen can have a Z number of 8, I believe. 8 protons. So that means the ground state neutral atom will have 8 electrons. Right? So you can have 2 there. We got room for 6 more. So you can have 2s, 2 there. That's 4. We can have 4 more. So how many goes in the P? P can have a maximum of 6, so you can put 4 in here. So that's the ground state neutral electronic configuration of the oxygen atom. Okay, what we've just described is Hund's rule. Hund's rule simply says that the lowest energy configuration of an atom is, well, actually, I take that back. That was the Aufbau principle, excuse me. Hund's rule goes one step further. Hund's rule says that if you have subshells available, like X, Y, and Z, then you fill those 1 electron at a time. So let's take this P. You can have a piece of X, a piece of Y, and a P sub Z. Okay? And if you have 4 electrons that go in there, Hund says that you have 1 here, 1 there, 1 there. You got to get those put in first. Then if you have any left over, you can pair them up. So that would be a more refined structure for oxygen and its p orbital. You have 2 in this one, 1 in that one, and 1 in that one. Now, why is that important? It's important because knowing this helps explain some of the physical and chemical characteristics of oxygen. We haven't talked about them yet, but we will. So that's Hund's rule. You can't pair up electrons within a subshell until you have at least 1 electron in each of the subshells. Then you can go back and start pairing them up. So that's what this represents. The authors like to use these boxes with arrows in them. That's too much. I don't want to write all those boxes. So I just put a line and an up arrow or a down arrow. Plus 1/2, minus 1/2. Spin. Okay? So that's oxygen. And that's known as the electronic configuration or the orbital diagram. It's a shorthand way of describing where the electrons are in the atom. Now, another concept that you may have already been introduced to in some other classes. I think anatomy and physiology do it when they talk about, they have a little blurb on chemistry, the importance of the valence electrons. The valence electrons help us do a rough approximation or a prediction for how atoms are going to react with one another. Simply put, the number of valence electrons are those that are all in the same energy level, the same principal quantum number. So for oxygen, that's 2 plus 6 is 8. So the valence electrons in oxygen are 8 in number. Let's see. We'll say more about that later. So here we talked about the structure, and I've alluded to that already. So let's see. I think we're going to have some examples. Yeah, we got an example there. So notice the way this chart is set up. From top to bottom is the principal quantum numbers, 1 through 7. That covers everything in the periodic chart. Then you write the possible configurations that are available at those energy levels. For n equals 1, 1s is the only one available. For 2, you've got s's and p's. For 3s, you've got spd. Right? For 4, you've got spdf. For 5, theoretically, you would have 5 possibilities, S, P, D, F, and G. But as it turns out, we don't need G. So that's why G is left out. And for 6, you actually only need S, P, and D, and for 7, S and P. So how do they fill? Well, they fill by drawing a diagonal from upper right to lower left. So here, 1s, that's a no-brainer. There's only one of them. 2s occurs there, and then you go out to 2p, and you draw down to 3s. So up to this point, you've got, they're in order, 1s, 2s, 2p, 3s, and then 3p, of course, is still in order. But when you go past 3p, you get to 4s before you get to 3d. And this is based upon lowest energy level for the electrons that are inserting as we build atoms. So 4s is actually at a lower energy than 3d. And if you look at your periodic table, let's go back. There's your 4s. And notice that when 4s fills and you head for the other side, well, there's 3p. Let's see, 3p, 4s. Instead of going to 3p down to 3d, we went to 4s first. 3p to 4s, then 3d, then you can go to 4p. Where do you go from here? Well, the diagram says from 4p here, you go to 5s, and then you go back to 4d. So 4p, 5s, 4d, then 5p, and then where do you go from there? 5p, 6s, right? So we go from 5p to 6s, and then we go to 4f. Oops, wrong way. 6s, we go back up to 4f and start filling the f's. Okay, so you can use this chart, which I believe is in useful information. I'm not sure. I don't have that copy with me. But if you know the structure of the periodic table, you don't need it. You just follow along, and knowing where everything goes in which orbitals, you say, okay, I'm here. That means I'm filling 4s, and everything up here in its order has been filled. And once I get 4s to go, I need to go to 3d. Right? So if we were to write something that had 4s and 3d available to it, we would go along here, and then we go 4s here, and then 3d. We wouldn't put 3d on this side because we're going in energy level order. And if you know how the periodic table is structured, then you can do that easily. Okay. Valence electrons, periodic table, Aufbau Principle. And of course, we're out of time, so you won't hurt my feelings if you have to go. But I want to at least show you one of them. So let's take sulfur. How many electrons are in the neutral sulfur atom? We look at your periodic table, right? Find sulfur, it's underneath oxygen. It has 16 protons. So we need 16 electrons. Okay? So how are we going to start? Right? 1s, 2s, 2p, 3s, 3p, and let's see how many we got. 2, 4, 10, 12. So we need 4 more. They can all go into this next one. All right. So if we look at the periodic table, let's see. Let me try it with this one. What have we filled so far? Well, if you just follow along, we filled the 1s. Then we went to 2s. Then we went to 2p, filled it up. Then we went to 3s. Then we went to 3p. Went over to sulfur. It's got 4 electrons in it. Notice 1, 2, 3, 4. From aluminum over to sulfur is 4 electrons in the p orbital. So if you know how the periodic table is structured, it's very simple to write the electronic structure of your atom. Let's do barium, because it's a much bigger atom. And rather than write the whole thing out, barium has 56, right? Maybe I better write it all out to make the point. I'm headed somewhere with this. So 1s, 2s, 2p, 3s, 3p, okay, 4s. Now where do we go? Well, 4s is right down here. And where do you go from 4s? You hit into 3d. Notice that this says 4 on this level, but when you get to the transition elements, you're not 4 anymore, you're 3. So you back up 1, 3d. So 3d, how many can we have in d? 10. Then we go back to 4p. Okay, so now at 4p, we are all the way over here to krypton. Now go back over here to rubidium, and we're going 5s, 4d. I'm going to swing back around. 5s, 4d, 10, and 5p, all the way to the end, right? And now we're back at 6s. And barium has 2 s electrons in it because it's in the second column in the 6s level. All right, now that should be barium. Let's count. Right. 2, 4 plus 6 is 10. 2, 4 plus 6 is 10, that's 20. 10 more is 30. 40. And then, let's see. I got messed up. 2, 4, 10, 20, 30, 36, 38, 48, 54, 56. So we have all of our electrons accounted for. Now, there's a shorthand way to write this. And the way to do it is you go to the element that you're trying to draw, and you go backwards until you find a noble gas. So we'll go backwards here. That means we have to go back up to this level over here. Xenon 54. And beyond xenon is 6s2. 2 plus 54 is 56. This is the shorthand way of writing the electronic configuration for barium. Why can we do that? Because the noble gases are completely filled. They're happy. They don't react. So none of the electrons in the noble gas configuration are available for reaction anyway, right? So we can write them separately like that. It's only when you need access to the lower level electrons for some exotic reason that you need to write them out completely. Okay, so there's sulfur, and we're saying sulfur can be written that way too. If you go back to neon, then you can just write, and notice that neon is represented by 1s2, 2s2, 2p6. Barium, there's your xenon. Europium is a little more complicated, and I'm not going to bore you with that one. But it also is xenon, and then 6s, and then 4f, because once you get into the 6th level, right, you work your way over here, lanthanum and everything following lanthanum is actually filling f orbitals. So europium, let's see, where is it? Here it is, europium. So it's 1, 2, 3, 4, 5, 6, 7. Actually, it's lanthanum 1, 2, 3, 4, 5, 6, 7. So 4F7. And notice that when we went to F's from 6, you subtract 2. And that all goes back to that Aufbau principle, because we had to back up 2 levels to get back to F. Okay. Periodic trends. So now that we've got our table set up, our periodic table set up, and we know how it's structured, then we want to use it to say something about elements. And we're going to talk about 3 different trends that can be derived from the periodic table. One is the ionization energy, one is electron affinity, the other is atomic radius. There are other trends that are available, but those are the 3 major ones. And we're not going to go beyond that. We just need to define what our terms are. What does it mean? So ionization energy, you always start with the neutral atom, the neutral element, and it has to be gaseous. It has to be in the gas phase. Right? For some elements at room temperature, it's already done. For some are liquid, it takes a little heat to make them gas. For some, like the metals, definitely, it takes a lot of energy to get them to the gaseous state. Now, why do we want to do that? Why do we need to get them to the gaseous state before we can say anything about their ionization energy? In other words, the energy required to remove an electron from an atom. That's the ionization energy. Well, if you start with the ground state atom in its standard state, if you start with a metal, then most of the energy you're going to put into the element is just to separate the atoms. You haven't touched the electrons yet. So we want things in the gaseous state because at that point, they're virtually independent atoms. That's the way gases are. So any energy you add beyond that goes into removing an electron. And that's why we write it this way. This is X represents any element in the gaseous state. We add energy and we get a singly charged element, an ion, plus the electron that's been removed. Now that's for the neutral atom. You can also say ionization energy for any of the ions if there are enough electrons, right? You can only have 1 ionization energy for hydrogen because it's only got 1 electron. But for helium, you can have 2 ionization energies. Or for magnesium, it's easy to have 3. Right? Magnesium's got 20 electrons, so you can go really high with that one. But we're just going to talk about these first 3. So the ionization energy, even though we didn't write gas in here, believe me, that's a gas, and this is a gas as an ion. And this is the amount of energy, kilojoules per mole, for the first ionization energy. And the first ionization energy always starts with the neutral atom. Second ionization energy then will be the second electron removal from an ion. Notice it takes a little more energy. Makes sense, right? Because you've already removed 1 electron. Now you have an excess of 1 plus charge hanging on to the rest of the electrons. So it takes more energy to remove that second electron. Then here we're moving a 3rd electron. And notice the energy jumps way up. Now, why is that? This goes back to the concept of the valence electrons. Right? So if you have magnesium, and let's see, right next to it is sodium. And here, magnesium has 3s, 2 electrons. And then what does it have next? Well, the next is 3p. Beyond that. What's behind it? Well, behind it is 2p. Right? So behind it would be neon. Now, the reason I'm putting that up there like that is to help you visualize. If you're removing electrons here, there are no p electrons. That's just saying that's what's beyond it. But if you remove one here, you still got another valence electron. So magnesium has 2 valence electrons available. And while the second one may take more energy, it's a small stepwise increase. In this case, double the amount of energy. But once you remove the valence electrons, what's next? The only thing available after that is what we call the core electrons. And the core electrons are bound very tightly. Why? Because they fill their orbitals completely and they're chemically happy. You get to a noble gas configuration. That's why noble gases don't react, because they don't want to give up electrons. They don't want to accept electrons. It takes a lot of energy to do either add or extract electrons. So once you get past the valence, then the energy required to remove an electron goes way up fast. Right? And this time it's 6 times as much energy. Not just double, but 6 times. Not quite 6, maybe 5. Okay, so what's the trend? Well, the trend is, and remember, these are groups and these are periods, right? From left to right is a period. So as you go across from left to right in the periodic table, the first ionization energy increases. And that's essentially due to the fact that you're adding protons. There's a stronger nuclear charge that's holding on to those electrons. And since all of the electrons in the valence shell are at the same, or roughly the same energy level, then they are not shielding one another from the nuclear charge. So when you remove one, it's like they're all, it's every electron for himself. So as you go from left to right, the effect of increasing nuclear charge is the dominant effect. And as you increase that positive charge in the nucleus, you make it more difficult to remove that first electron. That's the reason for the trend from left to right. But you can also talk about trends from in a group, top to bottom. Let's see. Left to right, first ionization energy in the same principal coordinate. Well, I thought we were going to get a I'm going backwards, sorry. There we go, top to bottom. Sorry, I was going the wrong direction. Top to bottom, as you go from top to bottom, the first ionization energy decreases. In other words, it's easier to remove an electron as you go down in a group. And that's primarily due to the fact that the energy levels put the outermost electron, the valence electrons, are farther from the nucleus. They don't feel the positive pull of the nucleus as strongly as the inner electrons do. So those outer electrons in the lower portions of a group are much easier to remove, right? So the trend is from bottom to top increasing and from left to right increasing. So for the whole periodic table, the trend is then from lower left to upper right is increasing first ionization energy. Okay. There's also a measure of shielding that takes place in the group. So as you move down, those electrons at lower energy level are taking the brunt of the attraction from the nucleus. So the outer electrons don't feel the positive charge as much for that reason too. Not just distance from the nucleus, but shielding from inner electrons. And this is just a chart to give you an idea of the trends, right? If you follow along, look at the look at the noble gases as a group. And as you go down in the group, from helium, neon, argon, krypton, xenon, radon, the first ionization energy decreases. You can do the same thing for fluorine, chlorine, bromine, and they don't show iodine, but the first ionization energies decrease. Or you could pick a metal. Let's pick, okay, we've got some in green here. Lithium, sodium, potassium, rubidium, cesium. So as you go down in that group, the first ionization energy decreases. You get some reversals, like here if you're going from beryllium to boron, that's left to right, right? Beryllium its valence electrons are all s electrons, whereas boron has p electrons. P electrons are farther from the nucleus. Their general density is because of that dumbbell shape. So when you're talking about the first ionization for energy for a boron, then you're seeing a lower value because it's removing a p electron rather than an s electron, because an s electron penetrates toward the nucleus and feels a stronger tug. Right, so the first ionization for beryllium is higher than it is for boron. And you see that trend all the way across. Here's magnesium skipping over to aluminum. Aluminum has a lower ionization energy. If you go from zinc, which is actually a d orbital, but you're going to the next highest one, which is gallium, it's also going from a d orbital to a p orbital, and the p orbital here is a little bit higher energy than the 4p for gallium is a little bit higher energy relative to the nucleus than the Z 3d orbital. Plus, the d orbitals are filled at zinc, and that makes them happy. So the next one you're talking about gallium is 1 p orbital electron. That's it's lower energy, easier to remove. Right, so you see those reversals, and the structure of the periodic table and the theory that's behind it explains why that is. So this is just a refresher on what we were just talking about. Why is the graph of ionization energies versus atomic numbers across a row not linear? Well, you get electron repulsions is the primary reason, because as you add protons across a period, you're also adding electrons, and they tend to repel one another. So you would expect the first ionization energy to increase from left to right, but it's not linear. Where are the exceptions? Well, we talked about beryllium to boron. We didn't talk about nitrogen to oxygen. That's a little more difficult to gather from the periodic table itself, but it's doable. So from nitrogen to oxygen, we're talking about 2p. Nitrogen and oxygen. So we have 2p orbitals here. All right, I'm not going to fill the rest of it in. You can look at the table and see that that's the 2p is part of their valence structure. And you can have 3 possible suborbitals. But how many electrons are in the nitrogen p orbital? Count from the left. From boron, you have 3. So there are 3 electrons, like that, like that, like that. Okay? Oxygen is one to the left, right of nitrogen. So it's one more electron. So it goes like this, like this, like this, that. So while we would expect from left to right as a general trend, oxygen should have a higher first ionization energy than nitrogen, it doesn't. It has a lower one. And here's why. Once you know how the electrons are filled in the orbitals, these are in separate suborbitals, whereas these two electrons have to occupy the same suborbital, and they repel one another. So one of them is much easier to get out. There's a repulsive force there that makes it easier, less energy required to remove that electron. So that explains why oxygen has a lower first ionization energy than nitrogen. And that's primarily due to electron repulsion. So which one of these, sodium or chlorine, requires more energy to remove an electron? Okay, well, we can look as a general trend. If the elements are farther apart from one another on the same period, then you can generally say that the one to the farthest right will have a higher first ionization energy or more energy required. So chlorine is way to the right of sodium. We would expect chlorine to have a higher first ionization energy. And that in fact is true. How about lithium and caesium? Well, lithium and caesium are in the same group, the alkali metals. So the trend there is if you go down, you have lower ionization energy required. So to answer this question, which one has more? Well, the one that's highest up in the group, which is lithium. So which one of these has the largest second ionization energy? Lithium and beryllium. Lithium and beryllium are neighbors. Lithium is an alkali metal. Beryllium is an alkaline earth. Right? So, what are its valence electrons? Well, lithium has a 2s1. Right? It's in the first column, and it's second energy level, so it's 2s1. Beryllium is right to the right of it. It has 2 electrons. Okay? So, when you remove 1 electron from lithium, what do you get? You remove that electron. If you try to move a second one, where is it coming from? It's coming from a 1s. So in order to remove the 1s electron takes much, much more. That's the core electron. Whereas beryllium is still, it's got another s electron. So it takes less energy to remove that second one. So in this case, lithium should have the higher, the larger second ionization energy. Because with lithium, the second electron is digging into the core electrons. And here's a chart, came out of your textbook, that illustrates, as you go down, sodium only has 1 valence electron, so when you take the second one out, it takes 10 times as much energy. Magnesium, we talked about that one earlier. You can get the first 2 off relatively easily, but the third one's in the core. So all of these examples are showing you that the real jump in energy required to remove that electron is coming from the core removal. Okay, that was ionization energy. And with ionization energy, you start with a gas, either the neutral atom or one of its ions, right? If it's second, third, or fourth ionization energy. With electron affinity, you also start with a gas, but you're measuring how much energy do you get back when an electron falls into the influence of that atom. That's what that means. Here, you add an electron rather than subtract an electron as a product. And you get that. So how much energy is added to the system and it's going to be a plus value, right? Add energy to the system is plus. Remove energy from the system is minus. So this value should be a positive value. And it has to do with how much energy do you, no, excuse me. I misspoke. Ionization energy is a positive delta H because you have to add energy to the system to remove the electron. Okay, let me say that again. Ionization energy is an endothermic process because you have to add energy to the system in order to remove the electron. Whereas electron affinity is an exothermic process. So when the electron is added from infinity down to whatever energy level is available, you get energy back. So that's going to be a negative value or an exothermic process. So for these negative values, the more attraction there is for the electron to be added to the neutral atom, the larger the negative value, the more negative the value will be, the more exothermic the value will be. So the stronger the attraction, the more negative the value. So what are the trends? Well, from left to right, as we go across from left to right, the electron affinities become more negative, right? So the attraction is much stronger, say for halogens, than it is for alkali metals. From top to bottom, the electron affinities become more positive. That is, they're less likely, as you go down a group, to be attractive to electrons. And that's because that the influence of the nucleus is shielded by lower energy electrons that are already there. Okay. So what does that mean for electron affinities? Well, the electron affinities are more negative as you go from lower left to upper right. So if you think of it in terms of you get more energy back from lower left to upper right. So the strength of attraction as measured by the negative number is from lower left to upper right. A similar trend to ionization energies. Okay, atomic radius is the last one. And all we can do is say what the trend is and then try to rationalize it. In general, as we go from left to right, the atomic radius decreases. So what do we mean by atomic radius? The distance from the center of the nucleus to the outermost expression of electron density. That's atomic radius. And we're talking about a neutral atom. So anything that would cause the electron density to be drawn toward the nucleus would shrink the size or the atomic radius of the atom. So that doesn't beg the question. It points a finger at nuclear charge. So the higher the nuclear charge, the smaller the atomic radius should be. And as we go from right to left in a period, you have increasing nuclear charge, which is not shielded by lower level electrons. And that increasing charge tends to draw those electrons closer to itself. So the trend from left to right is decreasing atomic radius. Now, if you go down in a group, the primary influence on atomic radius there is which energy levels are occupied. And as you go down a group, you have higher and higher level energy levels occupied by electrons, which means they're way out here. So you might have the first energy level here, second here, third here, as you go down. So the atomic radius decreases as you go down or increases as you go up. So the trend then up and to the right of decreasing radius, but from upper right to lower left, increasing radius. And this is just a pictorial representation, right? From left to right, lithium, beryllium are really big compared to the boron. Notice that what we're looking here, they left out the transition metals, right? They don't start till down here, right? Up here, it goes straight across with no transitions in the middle. But when you get down here, we skipped over the transition metals. And the reason for that is the transitions are like, they're a universe all to themselves because they're dealing with d orbitals. And they don't fit the pattern very well. So for the trend, it's more readily evident for atomic radius size. Atomic radius is more evident in its trends when we're looking at the representative elements only. And I say representative elements are first two groups, last six groups, excluding the transition elements and the lanthanides and actinides for that matter. They do have, you can explain how they behave, but it's not a general trend that's across the entire periodic table. Okay, which one of these would be larger? Well, let's see. If we're going from left to right and we're in the same period, sodium and chlorine in the same period, right? Yeah, just checking. Then the one on the farthest right should be the smallest. So the one on the left would be the largest, sodium. If we're in a group, which one's larger? We're going from lithium down to cesium. Cesium is in the same group as lithium, but it's much, much lower. It's filling higher energy levels. So cesium should be the larger one here. Okay, let me see. Well, I didn't drag out my copy, so I'm not sure how far I am to the end, but I need a short, like a 3-minute bathroom break. I'll be right back. Okay. Oops. Messed up my position in here. That should do it. All right. So, let's see. I'm going to try something here. Indulge me for a moment. Nope, that's not what I want. All right. Okay. So let's get back to our concept check. So let's think about the orbitals. The same principal quantum number and angular momentum quantum number, 1s, for either the hydrogen atom or the lithium atom. Which one is larger? I alluded to this earlier. They may have the same number letter, but that doesn't mean they're the same physical orbital. They'll have similar shape because they're both s orbitals, which is spherical. They'll have generally similar energy levels because they're both principal quantum number 1, but they should have a different size. Now, why is that? Because hydrogen only has one proton pulling on that orbital and the electron that's in it, whereas lithium has 3 protons pulling on that one. So the larger one should be the hydrogen, should it not? Right? It has less of an attraction. There's less draw from the nuclear charge for the hydrogen atom as the lithium atom. Which is lower in energy. Lower in energy refers to which one houses electrons closer to the nucleus. That's lower energy. So the larger orbital puts your electrons further from the nucleus, say farther from the nucleus. So the smaller orbital will bring them closer to the nucleus, would be lower energy. So that makes lithium should have the lower energy 1s orbital. Okay?
At room temperature, the metallic element molybdenum exists as a solid crystal. Metallic crystals behave like a three-dimensional array of cations surrounded by a sea of electrons. A molybdenum crystal can be used to estimate the atomic radius of molybdenum atoms. The distance between nuclear centers in molybdenum is 278 picometers. So the atom radius is estimated to be 139 picometers.
Okay. The key to that statement is estimated. It's still a mystery to me, in some cases, how the spacing and the radius is determined. I'm assured that, especially for solids, crystalline solids, I can understand that, because crystalline solids can be analyzed by X-ray diffraction, which is extremely accurate and reliable. So when you have a metal like this and you use X-ray crystallography, you can get extremely accurate measurements of the spacing of the atoms. When you're talking about liquids and elements that are standard temperature and pressure are liquids or gases, then it's a little bit iffy. I'm not too sure how they manage that.
At room temperature, the halogen element chlorine exists in the gas phase. Gas phase molecules are relatively far apart, since gases have low densities. Molecules move in straight lines until they collide with container walls or other molecules. The diatomic chlorine molecule can be used to estimate the atomic radius of chlorine atoms. The distance between nuclear centers in chlorine is 199 picometers, so the atom radius is estimated to be 100 picometers. At room temperature, the halogen element chlorine is...
Okay, so there, I'm not too sure about their how they managed to estimate that. I mean, if I dug into it a little more, maybe I could understand how they manage that. But well, at this point, we'll just have to take it on faith that the diameter of the molecule is about 199, so the atomic radius of chlorine is about 100 picometers. What's a picometer? All right, millimeter is 1,000th of a meter. Milli. Okay. Nano. Nanometer is about a billionth of a meter. See that meter just right here. A picometer is another 1,000 times. Right? Or 10 to the minus 12 meters. So we're talking about really small distances. Okay, let's see if we can arrange these elements in order of increasing ionization energy. Right? Remember the trend. Lower left to upper right is increasing ionization energy. Or across left to right a period, or bottom to top would be increasing. So let's see, oxygen, fluorine, and sulfur. Oxygen, fluorine, and sulfur. All right. Let me see if I can use this, if I can get it close enough. Oxygen, fluorine, and sulfur. You notice that oxygen, fluorine, and sulfur are right here close. So we know that fluorine is going to be a higher ionization energy than oxygen. And since fluorine and oxygen are both above sulfur, they should both be higher. So we should say increasing would be sulfur, oxygen, fluorine in that order. The ionization energy of fluorine is higher than oxygen, which in turn is higher than sulfur. How about atomic size? The trend is just the opposite. They get bigger in the opposite direction. Okay. So what have we learned about the periodic table? The chemistry, and I may not have emphasized this enough, but the chemistry of elements is due primarily to the number and the type of valence electrons. That is, those electrons that are all at the same energy level and available for a reaction, because they are the outermost electrons, right? They're the electrons that atoms encounter first when they meet one another. The electronic configuration, I did make a point of this one, that can be determined from the periodic table itself and the way it's organized. So you don't have to fret about writing electronic configurations if you know how the periodic table is set up. It's purposely set up that way so that the configurations can be written easily and you can understand chemical trends based upon the electronic configuration. We didn't mention this earlier, but certain groups of the periodic table have special names, right? And we've made mention of that from the very beginning, right? If you start from the right, of course, the noble gases, the halogens here. To the left of them, oxygen group, which are called the chalcogens, C-H-A-L. The nitrogen group is the pnictogens, starts with a P, a silent P, N-I-C-T-O, pnictogens. Carbon and boron don't have special names. Then over here on the right, you got the first group, which is the alkaline metals, and the second group is the alkaline earths, or sometimes called the alkaline earth metals. Oh, and then there are the lanthanides, which is the top series of elements where we're filling the f orbitals, and then the actinides below them. Oh, don't forget the transition metals. Okay. So there they are. And probably would have been easier to do it this way. We left out the basic division in the periodic table between metals and nonmetals. That's not shown here, but if you start just below boron and you go across, and then you start stepping down, step down, down, over, down, over, down, over, down, over, down. If you put a black line in there, that delineates nonmetals to the right, metals to the left. Okay. Metalloids. Metalloids are given that name because sometimes they behave as metals. They want to give up electrons. Sometimes they behave as nonmetals. They want to accept electrons. And those metalloids are very useful in the semiconductor industry because they can go both ways. That's all I can say about that because I'm no expert of semiconductors. Okay. We start to get into characteristics of the groups, but I'm not going to labor that point. In fact, I probably should get rid of this slide altogether. If we're going to talk about characteristics of groups, we need to do all of them. So rather than get into that can of worms, we just don't think about these right now. Just cover everything up to this point and you'll be good. That and work on your review document. Be ready to talk about it on Thursday. And then we'll prep for the next exam a week from today. Okay, we'll stop the share and open for questions.